Let us look at the weak duality condition. So we have already seen so far that f naught of x tilde is greater than equal to g of lambda comma nu, where lambda is greater than equal to 0 and x tilde is feasible. Right, so this property holds. Now, based on this, we can actually define the so-called dual problem. So the dual problem is given by max of g of lambda comma nu over all lambda that is greater than equal to 0 and lambda nu. So I'm just writing down the implicit constraints as well, that lambda comma nu belong to the domain of g. So g depends on lambda comma nu, and wherever domain or g is well defined, that is where we want to have lambda and nu. Note that the objective here is concave, right? So the objective here is concave, and the other way of writing the same thing is that this is equal to minus minimum of minus of g lambda comma nu and lambda greater than equal to 0, and lambda comma nu belongs to domain of minus g, right? So that's another way of writing the same thing as a convex optimization problem. Now, what does the dual problem allow us to say? So remember that the primal problem was minimization of f naught of x over all x such that fi of x less than equal to 0 and hj of x equal to 0, x belongs to d, right? So this is the primal problem and this is the dual problem, and we have the result that f naught of x tilde is greater than equal to g of lambda comma nu for lambda greater than equal to 0 and x tilde feasible. Now in this inequality, observe that there are two sides. One side depends on x tilde, other side depends on lambda and nu. The left hand side does not depend on lambda and nu, the right hand side does not depend on x tilde. Therefore we can tighten this inequality, right? So if you have you have an inequality where you have two different functions or two different variables on each of the sides, you can tighten that inequality. How can you tighten that inequality? You could say that I will take the smallest value of the left hand side, so I will minimize this side and I will maximize this side. So that will be the tightest possible version of this inequality. So I will say that I will do minimize f naught of x tilde over all x tilde that are feasible, right? And that would still be greater than equal to the maximum of g of lambda comma nu over all lambda bar that are greater than equal to 0. And if you remember, this is nothing but p and this is nothing but d. So this problem is nothing but d, and I also add that lambda nu is in the domain of g. So this says that p is greater than equal to d. In other words, the primal objective, the optimum primal value that the objective function takes is always greater than equal to the optimal dual value that the dual objective takes. So this is called the weak duality. Now observe that in the derivation of the weak duality, we used no other properties other than the definition of the Lagrangian and the dual function. So sort of you can get the motivation behind why we defined the Lagrangian and the dual function in that way. We defined it so that we can arrive at this weak duality property. So the weak duality follows directly from the definition of L and dual function. And in fact, this weak duality is valid even for the extended real valued definition that we had seen. So for instance, consider that p equal to minus infinity, right? When p equal to minus infinity, we said that the problem is unbounded below. So minus infinity, what does it mean for minus infinity to be greater than equal to d? So this implies that d is equal to minus infinity. Now d is equal to minus infinity. Remember that d is a maximization problem, right? D is a maximization problem, or you could say that the corresponding minimization problem is the minus of this. So this value, if d is minus infinity, this value will be infinity, right? For a convex optimization problem to be infinity, it means that the problem is infeasible, right? So this implies that the dual problem is infeasible, right? So if the primal problem is unbounded below, it implies that the dual problem is infeasible from this definition. And likewise, if you have d equal to infinity, which is the opposite, which means that the dual problem is unbounded above, right? Because it is a maximization problem, so it could be unbounded above. It would imply that, so infinity, p is greater than equal to infinity, which means that p is also infinity. So this means that the primal problem is infeasible, right? So the weak duality and the definition of the Lagrangian links together the primal and dual problems in this way. And in general, the primal objective is always greater than equal to the dual. And this property holds even with p or d are infinity or minus infinity. And in fact, we define the duality gap. So the duality gap is defined as p minus d. So in general, the duality gap is always greater than equal to 0. So that is another way of stating the same property. So duality and weak duality property allows us to develop several kinds of bounds for various problems. Remember that at no point did we have to assume that the problem is convex. So we have derived everything so far while assuming that the problem is general. Even when the problem is non-convex, fortunately it turns out that the dual is still a concave problem, a maximization of a concave function, and therefore all these results continue to hold. And in fact, for any problem, even if it is non-convex, because the dual is a convex optimization problem, you can therefore solve it efficiently, and therefore you can always find d for any problem. Which means what? Which means that you can always find a lower bound on p for any problem, whether it is convex or non-convex. Let's take a simple example to demonstrate this idea. So let's consider minimize x transpose x subject to ax equal to b. So this is a simple example to demonstrate this idea. This is, by the way, if you recognize this, this is nothing but the least norm solution. So this is nothing but the least norm solution to the system of equations ax equal to b. Note that there are no implicit constraints in this case. So we can write L of x comma. So now there are no inequality constraints. So there is no lambda, and there is nu y to nu p in this case. So here let's say that A is in R p cross n, so that we have nu1 to nu p, and hence L of x comma nu is given by half x transpose x plus, I can write it as nu I times ai transpose x minus b, or I can write it compactly as nu transpose ax minus b. Now let us find out the dual function. In this case, the dual function would be a function of nu, which is in Rp. So dual function is given by min over x L of x comma nu, where x is any vector in Rn. So this is what? Now minimization of the Lagrangian, unconstrained minimization of the Lagrangian is easier than the constrained minimization problem that we were earlier dealing with. So oftentimes you will see that this problem can be solved in closed form, right? So in this case, for example, how do we solve this problem? So here Lagrangian is a quadratic function, and its minimum is given by, so we can just differentiate L with respect to x, and we will obtain x plus A transpose nu. So this equal to 0 is the nu, or sorry, is the x that minimizes L of x comma nu. In other words, we get x equal to minus A transpose nu, and if we substitute it back, we obtain that G of nu is equal to half nu transpose A transpose nu plus nu transpose A transpose minus A transpose nu minus B. So the first two terms will cancel partially, so we will obtain minus half nu transpose A transpose nu minus B transpose nu. Right, so this is the dual function, and therefore the dual problem is given by, so the dual problem is maximization of minus half nu transpose A transpose nu minus B transpose nu. There are no constraints on nu. Remember that we had a constraint that lambda is greater than or equal to 0, but we have no such constraints on nu. So nu is any vector in Rp. So this is the dual problem. In this case, actually you can directly also solve the dual problem. So the solution of the dual problem is also quadratic, and it's a maximization problem, and A transpose is PSD, so therefore the function is concave, right? So we can solve it by again taking the derivative. So we can take the derivative with respect to nu and set it equal to 0, which would give us minus A transpose nu minus B equal to 0, or nu equal to minus A transpose inverse B. So let's say that A transpose is invertible. If it is invertible, then nu is minus A transpose inverse B, and therefore this would imply that G of nu, so this is actually nu star, right? So G of nu star, which is equal to D, is equal to, so if we substitute this here, we would obtain half B transpose A transpose inverse B, right? So our result that P is greater than or equal to D is essentially saying that half X transpose X for any, let's call it X tilde, for any X tilde such that AX tilde equal to B is greater than or equal to half B transpose A transpose inverse B. So this is a bound that we have been able to obtain. So essentially we are saying that P, which is P, which is the smallest value here, is also greater than or equal to this bound. And that is an example of the application of weak duality. So this was really a simple example because there was no need for us to try to find a lower bound on this problem, on this least norm problem, but because we can directly solve it also. But this is just an example to show how the dual function is constructed and how do you have to calculate the dual problem. And in fact, in this case, if we don't know the primal, how to solve the primal problem, we can still figure out how to solve the dual problem, because in this case, dual problem is unconstrained. So generally, whenever you have a primal problem with affine constraints, the dual problem will be unconstrained and you can easily solve it. So that's all I have about weak duality and an example application. We'll look at more applications later.